Hello, myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about data representation. At the end of this video, the student gain knowledge about how numbers and text, special symbols can be represented and what are the number system and how the conversions from one number system to another number system can take place. So the main topics that can be discussed in this video are introduction, number system, complements, fixed point representation, floating point representation, and the examples. So data types can be found in the registers of a computer. So in a programming language, while defining a variable, various types of data can be used. So what type of value is stored on that particular variable, depending upon that the data type of the variable can be defined, like int, float, char, like that, string. So various data types can be used. But in case of computer organization, the registers can be used to store the data. So here the type of information that can be stored in the registers can be numbers, letters, or any discrete symbols. So the numbers can be generally used to represent with the number system. The letters and other discrete symbols can be represented with a code. The code can be the ASCII, American Standard Code for Information Interchange. So by using this standard code, the discrete symbols can be letters and discrete symbols can be represented in the registers of a computer. So the number can be represented with the number system. So here, while representing the number system, the radix or base is the major component of the number system. So what is radix means? A number system base or radix can uses distinct symbol for the digits. So how many number of digits can be represented by using that number system is the base or radix of that particular number system. For example, we are generally using the decimal number system. We can use the digits to, here are 0 to 9. So totally number of symbols we can use in these are the 10. So the base of the number system is the 10. In case of binary number system, 0 and 1 can be used. So here the base can be 2. In case of octal number system, 0 to 7 numbers can be used. So the base is 8. Here we can use 0, 1. In this 0 to 9 digits. In case of hexadecimal, totally 16 symbols can be used to represent. We can have the numbers 0 to 9. Remaining we have to use the letters A to F to represent the corresponding digits. So the radix or base can represent total number of symbols that can be used in that particular number system. We are having decimal number system, binary number system, octal number system, hexadecimal number system. How to convert from a decimal to other number systems? So consider a decimal number 17 and how it can be converted into the binary. So the binary number system can have a base value 2. With this 2, this number can be divided. So 17 can be divided and the remainder can be noted down. So until the last digit, the division can be performed so that the number can be undivisible and the remainder can be written from bottom to top, which is the binary number. So 1 0 0 0 1 is the binary number. Similar way, from decimal to octal, the base value is the 8. So the number has to be divided with the 8 and the remainders can be written from bottom to top fashion in order to get the octal equivalent of the decimal number. And similar way, the 16, the hexadecimal value can have a base value 16, so that the decimal number can be divided with the 16 and writing the remainders from bottom to top in order to get the hexadecimal equivalent of the decimal number. So in this way, the decimal numbers can be converted into the other systems. So let us take an example, conversion of decimal to binary number. So consider a number 10 with the decimal number system and you have to convert into the binary number system. So here the digit and it has to be divided with the 2 and we have to write the remainder. And this process has to be continued until the number should not be further divisible, and writing the remainder in a bottom to top fashion. 1010 is the binary equivalent of the number 10. In this way, the decimal to binary conversion can be take place. Similar way, you have to take a number and we can convert into the octal number system. So here 23 and we have to divide with the octal number system base value 8. Okay. So it can be string 2. So we have to write in 27 is the octal number equivalent. Next, convert the decimal to hexadecimal value. Take the 32 value of decimal and convert into the hexadecimal value. So 32, it can be divided with 16, 20. So 20 is the 16-bit equivalent. So in this way, the decimal number can be converted into other number systems. How the binary system to decimal can be taken place? We have to consider the digits and here the unit place value of the concerned number system can be connected. For example, take 1010 and it has to binary number system to decimal can be considered. This is the binary number. And here each digit can be multiplied with the unit value of that particular number system. So here this bit can have the positional value 2 power 0, 2 power 1, 2 power 2, 2 power 3. So you have to calculate 0 into 2 power 0, 1 into 2 power 1, 0 into 2 power 2, 1 into 2 power 3. So after adding these base values, we can get the 10. So it is the decimal equivalent of the binary number. So consider an example. For example, 1001, it is a binary number and we can convert into calculate the decimal equivalent. We have to write the positional values. So here 1 into 2 power 0 plus 0 into 2 power 1 plus 0 into 2 power 2 plus 1 into 2 power 3. So here this can be 1, 0 multiplied by anything 0. It can be 8. So 8 plus 1, it is of 9. So this is the decimal value of the binary number. Similar way, the octal number can be converted into decimal number by using the place value multiplied with the corresponding digit of the given number. So here consider the example, the octal number 143. So here 3 into 8 power 0, 4 into 8 power 1, 1 into 8 power 2. So the values can be added. You can get 99, which is the equivalent of the octal, decimal equivalent of the octal number 143. So now consider an example 112. This is the octal number and can be converted into the what is the decimal equivalent of the number. Okay. So here the number of digits are 112, which has to multiplied with the place values 8 power 0 plus 8 power 1 plus 8 power 2. So it can be 2. So it is 8. It is 64. Okay. So here by multiplying with the place value with the digit values can be written and can be added. So it can be of 74, which is the decimal equivalent of the number. Next, hexadecimal to decimal conversion. So here to represent the total 16 symbols, 0 to 9 are the digits, remaining are the A to F are the letters. So consider a hexadecimal number. So here E is the 14 and 7, 3, A is of value 10. So these can be multiplied with the face value 16 power 0, 16 power 1, 16 power 2, 16 power 3. So that we can get the result as, after summing it, this 41,854 is the decimal conversion. So how similarly we will take an example. Okay. So how we have to take an example. This is the hexadecimal number and we can convert into the hexadecimal. Take a hexadecimal number A1. This is the hexadecimal number. How it can be converted into the decimal 1. So we have to write the digits 1 into 16 power 0 plus A is of representing 10 digit 16 power 1. So it is of 16 into 160. Okay. So now we have to add, this is, okay. So now each digit can be written and can be multiplied with the place value of that particular number system. So it is unit place 16 power 0. It is ones place 16 power 1. After getting the terms, those can be added. Okay. So here we have to add this. Okay. Now the terms that we can get can be added. So this is the decimal equivalent of the hexadecimal number. In this way, from one number system to another number system, we can convert the values. What is the binary coded decimal? So here it is another means of representing the numbers. Not only the number system, decimal, hexadecimal, binary, octal system. With the binary coded decimal also, the numbers can be represented. What is BCD? Is a 4-bit equivalent of the digit, can be the binary coded decimal. For example, consider 0. In a 4-bit binary equivalent of 0 can be 4 zeros. And consider 1. 0001 is binary equivalent 4-bit code of 1. Next 2, 3, 4, 5, 6, 7, 8, 9. For 9, 1001 is the 4-bit binary equivalent of 9. In this way, the BCD can be represented. For example, if you want to represent 00, for each digit, the 4-bit binary equivalent value can be written. For 0, it should be represented with 4 zeros. So, 2 4 zeros can be written. For example, if you want to represent 15, the 1 binary 4-bit binary equivalent and 5 4-bit binary equivalent can be written. What is the 1 4-bit binary equivalent? 0001. And what is 5-bit binary equivalent? 0101. So, like in this way, the BCD values can be represented. If you want to represent 25 in the BCD, we have to write the 2's 4-bit binary equivalent. What is the 2's 4-bit binary equivalent? 0010. Next, for 5, what is the 4-bit binary equivalent? 0101. So, this is the BCD of 25. So, in this way, the binary coded decimal can be used to represent numbers. So, here the data type, the numbers can be represented by using the number system or with the help of BCD. Now, how the characters can be, special symbols can be represented. So, an alphanumeric characters is a set of elements that include 10 decimal digits, 26 alphabets and a number of special characters like plus, @, all these are the special characters. So, a special code can be used to represent this. That code is the ASCII, American Standard Code for Information Interchange. So, here we are having to represent totally 256 symbols. So, the code can be like this. Okay. So, here the numbers can be represented with the value of 48 to 57. So, here this is the ASCII code to represent. The ASCII code of 48 to 57 is used to represent the numbers. And the letters 65, ASCII code 65 is represent the capital A. So, 90 is to represent the capital Z. So, ASCII code of 65 to 90 is used to represent the capital letters. Okay. Now, the small letters can start at the ASCII code of 97 and the small z is at the ASCII code of 122. So, 97 to 128 ASCII code is used to represent the small letters. Okay. Like this, totally 256 symbols can be used to represent the varied alphabet and special symbols, all these characters. This code is called the ASCII code. What are complements? So, complement in the digital computer can be used to simplify the subtract arithmetic operation and also simplify some logical operations. Generally, for any number system, two types of complements are available. One is the base complement, that is the R complement, and the base minus 1 complement or minus 1 complement. For example, if you consider decimal number system, the base complement is 10 complement and base minus 1 complement, 9's complement can be available. If you take the binary number system, the base complement 2's complement and base minus 1, 1's complement can be available. So, for any number system, the base complement and base minus 1 complement can be available. So, if you take binary number, the 1's complement can be by interchanging 0 value as 1, 1 value as 0. So, here 000 10011 the ones complement can be 0 can be interchanged as 1 can be interchanged as 0, 1 can be interchanged as 0, 0 can be interchanged as 1. You can get the ones complement. 2's complement means 1's complement value plus 1. Then we can get the 2's complement value. So take here a binary number, and what is the ones complement of this number is by interchanging 1 as 0, 0 as 1. So 0, 1, 0, 1, 0 is the ones complement of the number. And 2's complement, how to get? Ones complement plus 1. So 1's complement is 0, 1, 0, 1, 0, and we have to add a 1 to it. So 1, 1, 0, 1, 0. This is the 2's complement of the number 1, 0, 1, 0, 1. And what is fixed point representation? So without a fractional part, any number that can be considered as the fixed point number. And these fixed point numbers can be represented by using 3 ways. One is signed magnitude representation, signed ones complement representation, signed 2's complement representation. So for example, consider a number 4. So this magnitude, the 4 equivalent can be 1. So this is the sign bit. So signed representation can be the to indicate this, if sign bit is on, it is a negative number. So here sign bit can be 1. So it is negative number, and the magnitude of this binary number equivalent in the decimal form is 4. So this is the signed magnitude representation. And here this is a positive number, the sign bit is off and used to represent the plus 4 value. This is the signed magnitude representation. Now consider an example. Here 60 value have to represent. The sign can be the positive, so that the sign bit can be the off. So 0 is to represent the sign bit, and this is the equivalent, binary equivalent of decimal number 60. Okay. So this implementation representation is called signed magnitude representation. Okay. And signed ones complement means this is the 60 representation, and the ones complement of this number is so positive 60 plus ones complement magnitude can be represented in the ones complement, and 2's complement along with sign can be represented. Now consider, for example, the 4 value. The 4 value, this is the negative 4 value representation, and this is the positive 4 value representation. This is the signed magnitude form. For example, to represent the plus 4, using the 0 is the sign bit, and the magnitude okay, and the magnitude here to represent the 4 value, this is the plus 4 representation. So in the signed ones complement form, to represent the plus 4, 0, and ones complement of this 4 can be used. 1, 1, 0, 1, 1, 1. So this is the signed ones complement representation to represent the 4. And signed 2's complement means for this we have to add a 1. So that is 111, 0, 1, 1 plus 1. 0, 1, 0, 1, 1, 111. So this is the 2's complement of 4. So these bits are used to represent 2's complement and this is the sign. So this is the 2's complement representation, signed 2's complement representation. In this way, the fixed points can be represented. What is floating points? The numbers with fractional part can be treated as the floating points. So these floating point numbers can be represented by using two parts. One is a mantissa m and an exponent e. So these two parts can be generally represented mantissa m into radix power exponent e. This is the form to represent the floating point representation. So here a standard IEEE standard 754 can be used to represent the floating points. So here 0 represents a positive number, 1 represents a negative number. So here a biased exponent, the exponent field need to represent both positive and negative exponents. A bias is added to the exponent in order to get the stored exponent. And normalized mantissa. Mantissa is part of number in scientific notation and consists of its significant digits. So here this form m mantissa into base power exponent form is the standard form to represent the floating point. By using the IEEE 754 representation, single precision and double precision floating points can be represented. The single precision floating point can be represented with 32 bits. The 23 bits are used to represent the mantissa and 8 bits are used to represent the exponent. 1 bit is used to represent the sign bit. So this format is IEEE 754 format to represent the single precision representation in order to represent 32 bits. Next is the double precision representation. Double precision representation can hold 64 bits and mantissa can be used to represent 52 bits and exponent can be used to represent 11 bits and 1 bit is used to represent the sign bit, whether the number is positive or negative. So these are the IEEE 754 single precision and double precision floating point representation. So in this way, in this video, how to represent the numbers by using the various number systems like decimal number system, binary number system, octal and hexadecimal number system. And another alternative way to represent numbers is the BCD, binary coded decimal. How numbers are represented in the BCD and how alphabets and special symbols can be represented with the help of the code ASCII code. And what is fixed point and what is floating point and what are the ways to represent these fixed point and IEEE 754 format to represent the floating point as single precision and double precision. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.